Hi, my name is Ben Biggs, and for my project, I decided to try to evolve a defender for the game of Hnefatafl. Now, Hnefatafl is not well known, but it was an important game in Viking culture. As you can see in describing a noble Viking, Earl Rognvaldr colleague said, first, I play Tafl enthusiastically. Now, board games like checkers, chess, shogi, and go have well-defined, simple sets of rules and are constrained to a small board. And yet, nobody knows how to play any of these games perfectly. This is because the number of possible games grows exponentially with the number of moves allowed on a given turn. In fact, it's estimated that there are more possible games of chess than there are atoms in the observable universe. Naturally, a large number of those possible games are composed of bad moves if the goal is to win. This makes board games and even some video games excellent proving grounds for machine learning algorithms. Now, while I did not consider algorithms such as Monte Carlo tree search throughout the course of this project, Monte Carlo tree search has been used extensively in developing agents to play chess, shogi, and go, with go being the crowning achievement. I also didn't use alpha-beta search to prune the tree of possible moves and states throughout this project. Instead, I focused my efforts on developing a board evaluator that allows the white team, shown in the picture, to hopefully win the game of Hnefatafl. As you can see from the board, the game of Hnefatafl is unique in that it's not symmetrical in the way checkers, chess, shogi, and go are. I'm not aware of other games like it, although Hnefatafl is better understood as a group of Tafl games. I was able to find one paper that the majority of this project is based on. Admittedly, the methods that I've used over the course of this project are fairly outdated, but as you'll see, the outcome is promising, and I think some more mainstream methods, like those used by AlphaZero, would lend themselves fairly immediately to the game and games like Hnefatafl. I, however, am just one student with limited time and resources, so I kept things fairly simple. In fact, the methods that I used throughout this paper are more like those used in the development of Blondie 24 for checkers in the early 2000s than they are like Stockfish or any of the Google Alpha programs such as AlphaLee, AlphaGo, or AlphaZero. Now, the reason that I chose to develop a defender for Hnefatafl is this. I received the Hnefatafl set shown in the picture for Christmas and started playing with a lab mate. At first, it seems that it was impossible for the brown team to defeat the white team. After several weeks of playing, though, we discovered some very simple strategies for the brown team, and the tables turned. All of a sudden, it was impossible for the white team to win. So naturally, I wanted to make a defender that can beat the attacker, or a white team that can defeat the brown team. And the attacker is employing the simple strategies that we discovered. So let's take a look at the game itself. The specific version of Hnefatafl of interest to me is called Fetlar Hnefatafl. In Fetlar Hnefatafl, the white team, or the defenders, have 13 pieces, with one of those pieces being the king at the center of the board. The goal of the white team is to move the king to one of the corner squares, called a burg. Each piece moves like a rook in chess, but captures aren't quite the same. In Hnefatafl, a piece is captured if it is sandwiched between two pieces from the opposing team, or a single piece from the opposing team and a restricted square, such as the center square called the castle, or one of the burgs. Multiple captures are allowed, but a piece can't commit suicide. That is, a piece can move into the space between two enemy pieces without being captured. The king is different from the other pieces, though. To capture the king, the enemy pieces must surround him on 4 sides, as shown in the pictures. Now, one side can be the center square or castle. If the king is captured, the attackers win. It's also considered a win for the attackers if they're able to surround the defenders such that no defender can reach the edge of the board. If a board state is repeated, the game is a draw. Also, if one team is able to surround the other such that there are no valid moves available on their turn, the surrounding team wins. Now, due to the uncommon nature of the game, I had to develop my own API to implement the game logic for Fetlar Hnefatafl. So if you ever find yourself needing Fetlar Hnefatafl game logic, You can find it now on the Python project library and install it with pip. Now, after implementing the game logic, I needed to develop an attacker that could utilize the simple strategies that I had discovered. Now, before I mention what those strategies are, I want to make it clear why this step is so important. Now, in an attempt to see what the game balance was, I simulated 1,000 games between two players that choose one valid move uniformly at random on their turn. I found that out of the 1,000 games played in this manner, the defenders won 86.7% of the time, and the game ended in a draw 12.2% of the time. The attackers won only 1.1% of the 1,000 games played. So we needed an attacker that wouldn't choose moves at random simply because the defender wouldn't need to learn anything if it did that. So the strategies we implemented were the following. If the attacker can move a piece into one of the squares marked red without leaving a red square, they should do so. Doing this quickly stops the king from being able to reach any of the corners. The positioning of the red squares is important because no piece in a group of three, as the red cells are chosen, can be captured if the white cells adjacent to the corner squares are empty. Secondly, if the corners are filled and there is a piece that can move into a position adjacent to the king, one of the yellow squares pictured here, without leaving a red square, then they should do this. This strategy leads to king captures and thus attacker wins. If no desirable move is available, simply try to move a piece that is not on a yellow or red square at random. If there's no such piece, move a piece at random. Implementing this heuristic, the tables turned dramatically. Of 1,000 games that I simulated, the random defender won only 0.4% of the games played. Only 5.5% of the games resulted in a draw, and the attackers won an astonishing 94.1% of the games played. So now the defender really needs to learn something if it's going to not lose. So to develop a defender, I chose to closely follow the method proposed in the one and only paper that I was able to find that addresses the game of Hnefatafl, albeit a slightly different version than Fetlar. An agent has a neural network that it uses to evaluate the state of the game board. Each square of the board is an input to the neural network. Empty squares activate as zeros, while squares containing attackers activate as +1. Defender squares activate as -1, and the king square activates as -2. Now, because all captures occur in three square sandwiches and pieces can move like rooks, there are neurons corresponding to sets of 3 neighboring columns, 3 neighboring rows, and 3 by 3 blocks. So 9 column neurons, 9 row neurons, and 81 block neurons. There are 2 more neurons for the number of defender captures and the number of attacker captures. All of these neurons have the sigmoid as their activation function and feed into every neuron in the hidden layer. There are 10 neurons in the hidden layer, all of which have the sigmoid as their activation function and feed into the single output neuron. The output neuron also uses the sigmoid as the activation function. To train the neural network, I used an evolutionary strategy. At a high level, the evolutionary strategy works like this. I initialize K agents with their corresponding neural networks. The neural network parameters are all generated according to a normal distribution. After initializing these first K agents, or the K parents, I initialize K more agents with slightly changed versions of the parent neural network parameters. We now have K plus K agents, the parents and their children. We evaluate the fitness of all these agents, and the K fittest agents survive to be the parents of the next generation of agents. This process of survival of the fittest is repeated for an appropriate number of generations, with the hope that eventually some agents' neural networks will start to evaluate the board in a way that leads the agent to make competent choices. To evaluate the fitness of an agent, I had them play 3 games against the heuristic attacker and 3 games against random attackers. If the agent won, They received a score of 1 for the game and -1 if they lost. A draw resulted in a score of 0. The fitness of an individual is found as the sum of the scores from the games it played. So a perfect defender would have a score of 6. I ran the evolutionary strategy for 1,000 generations with 8 parents at a time and 8 children at a time. The figure on the left shows the average fitness of the survivors from each generation. The figure on the right shows the fitness of the best survivor. Early on, the defender was winning all games against the random attacker and losing almost all games against the heuristic attacker. This led to an average fitness of about 0 for the first while. After about 100 generations, though, some agents started to evaluate the board better, leading to increased fitness scores on average as the survivors passed on good traits. The average fitness increased to between 2 and 2.5, meaning that on average, the outcome of games against the heuristic attacker is converging to a draw instead of a loss. The fittest individuals are frequently able to win against the heuristic attacker with scores of 4, 5, and 6 occurring regularly. Increased population sizes are very important for this type of algorithm, so I'm sure increasing K to 100 or even 1,000 would yield much better results. However, I'm very satisfied with these results for the scope of this project. Thank you.